You know, inside a nuclear power plant, something that sounds like it's straight out of science fiction is happening right now. Tiny, invisible atoms are unleashing just an incredible amount of energy, and we're turning that fundamental force of the universe into the electricity that powers our lives. So, how on earth do we get from a single atom to the light in your room? Well, let's dive in and figure it out.
First off, we need to get a sense of scale here. So think about a chemical reaction, like a single molecule of TNT exploding. That gives off about 10 electron volts of energy. Okay, but splitting just one uranium-235 atom, that releases 200 million electron volts. And what's really wild here is just how huge that difference is. We're not talking about something that's twice as powerful, or even 100 times more powerful. Nuclear fission is literally 20 million times more powerful than a chemical reaction. And that mind-boggling amount of energy, that's why just 1 kilogram of nuclear fuel can generate as much energy as thousands of tons of coal. But, of course, that also presents a massive challenge. So how do we safely control and harness this incredible power without, it getting out of hand? Well, it all starts with one single fundamental process. The key to unlocking all that energy is something called nuclear fission. Simply put, nuclear fission is just the act of splitting an atom's core, its nucleus. For this, we use heavy, kinda unstable atoms like uranium-235. When its nucleus splits, it converts a tiny, tiny amount of its mass directly into a massive amount of energy. And it perfectly follows Einstein's famous equation, E equals mc squared. Okay, so here's how it works. Picture this. It all kicks off with a single neutron just flying through space. When this little neutron hits a uranium-235 nucleus, the nucleus basically swallows it and becomes super unstable. It can't handle it, so it immediately splits into two smaller pieces, releasing a huge burst of energy and, this is the most important part, 2 or 3 new neutrons. And these new neutrons, well, they're the key to absolutely everything that happens next. Now, splitting one atom is cool and all, but it's not going to power a city. To do that, you need to create a self-sustaining cascade of these splits, what we call a chain reaction. Remember those 2 or 3 neutrons we just released? Well, each one of them can now fly off and smash into another uranium nucleus, causing it to split and release even more energy and, you guessed it, more neutrons. And then those neutrons hit other nuclei, and so on and so on. It's like the ultimate set of dominoes, creating this exponentially growing chain reaction. Now, to control this whole process, scientists use a really critical measurement called the neutron multiplication factor, or just K. This number basically tells us if the number of neutrons is growing, shrinking, or staying the same from one moment to the next. It is the ultimate control knob for a nuclear reactor. So think of it like this. If K is less than 1, there aren't enough new neutrons and the reaction just fizzles out. If K is greater than 1, the reaction grows exponentially and uncontrollably. That's what happens in an atomic bomb. But for a power plant, the absolute goal, the sweet spot, is to keep K perfectly, exactly at 1. This creates a stable, self-sustaining reaction that produces a steady, predictable, and controllable amount of heat. Okay, so we've got our controlled chain reaction, and it's pumping out an enormous amount of heat. But how do we turn that heat into the electricity that, say, charges your phone? Well, the method is actually surprisingly old school. We're going to boil some water. A nuclear power plant is, at its heart, a really, really advanced steam engine. So this is the basic layout of a nuclear power plant. Now, I know it looks complex, but it really all comes down to just a few key parts. You've got the reactor core right in the center. That's where all the fission happens. The heat from that reaction is used to create steam, and that steam powers a turbine connected to an electrical generator. Let's just walk through it step by step. All right, here's the play-by-play. Inside that reactor core, the fission heats up water in a totally sealed loop called the primary circuit. This water is kept under insane pressure. So even though it gets incredibly hot, we're talking over 300 degrees Celsius, it doesn't actually boil. This superheated radioactive water then flows into something called a steam generator. There, it heats a completely separate secondary loop of water, causing that water to boil and turn into high-pressure steam. That steam then shoots out and spins a massive turbine, which in turn spins a generator, and voila, you've got electricity. And because those two water circuits never mix, the radioactive stuff stays safely contained. You know, when you really strip it all down, a nuclear power plant is just a very, very sophisticated and powerful way to boil water. Instead of burning coal or oil or gas, it uses the energy from splitting atoms to create the steam that generates electricity. It really is a 21st century steam engine, just powered by the atom itself. So, we've seen how this technology works, and its advantages are pretty huge. A massive amount of reliable power from a tiny amount of fuel with basically zero carbon emissions. And that's exactly why so many people see it as a key part of our energy future. But it's not without its challenges, and tackling those challenges is what's driving the next generation of nuclear technology. The whole industry really faces three major hurdles. First, you've got to ensure absolute safety and prevent any release of radiation. That means multiple, redundant safety systems. Second is the big one. What do you do with the radioactive waste? The long-term management and disposal is a huge challenge. And third, these traditional large-scale nuclear plants are incredibly complex, which means they are expensive and can take a decade or more to build. So one of the most exciting solutions that's coming up is the small modular reactor, or SMR. Think of these as compact, factory-built nuclear power plants. Because they're standardized and then assembled on site, the hope is to dramatically lower costs and build times. Plus, they're designed with these incredible, advanced safety features that can shut the reactor down automatically with no human help needed, making them potentially much safer than older, larger designs. And if we look even further into the future, we get to the ultimate goal, thermonuclear fusion. This is the complete opposite of fission. Instead of splitting heavy atoms, fusion combines light ones, like types of hydrogen, to release energy. It's the very same process that has powered our sun for billions of years, and it promises a future with almost limitless clean energy, no long-lived radioactive waste, and using fuel we can get from seawater. It's the holy grail of energy. From the controlled splitting of an atom to these futuristic designs that literally try to build a star on Earth, the story of nuclear energy is one of humanity's greatest scientific adventures. The power is there. It's locked away in the heart of every bit of matter. The real question for our future isn't just about unlocking it, but about how we choose to master it.